Welcome to section 1.5. This is about reduced echelon form. What is reduced echelon form, you might ask? Well, we're about to find out. Let's take a look at this section. Reduced echelon form. We're going to learn not only what it is, but how to get it. So let's check it out. After doing Gauss-Jordan elimination, if we were to get 1, 0, R, where R is some number in the first row, and 0, 1, S, where S is some number, then it would be very easy for us to write out the solution. The solution to this system of equations would just be x1 is R and x2 is S. Pretty straightforward. Or if we were to have something like 1, 0, 0, and then some number, I'm just calling it R, and then 0, 1, 0, some number S, and 0, 0, 1, and some number T. Again, we could very quickly write out the solution. It would be x1 is R, x2 is S, and x3 is T. Okay, but we can't always do this. We don't always get that nice, pretty little diagonal ones, that nice, pretty little set of diagonal ones. Particularly with rectangular systems, it's going to be impossible for us to get that nice, pretty design. So what we need is something to show us when an augmented matrix is as reduced as possible. Essentially, it's going to tell us when to stop if we're doing Gauss-Jordan elimination. Okay, so this is our motivation for having reduced echelon form, because reduced echelon form is going to be that state when a matrix is as reduced as possible. Okay, there's our motivation. All right, now what is it? Reduced echelon form. All four of these conditions must be met. Not just one, not just two, not just three, but all four at the same time. The first is that all rows that consist entirely of zeros have to be at the bottom. Okay, so if there is a row of zeros, or more than one row of zeros, it or they have to be at the bottom. Okay, if there aren't any rows of zeros, then you just go, oh yeah, sure, all rows of zeros, okay, well there aren't any, so we go to the next step. All right, second, in a non-zero row, so if you have a row that contains something other than zeros, the first non-zero entry from the left, so if we're looking left to right, the first thing we see that's not a zero is a 1. We call that a leading 1 because it's the first non-zero entry in a row. Right? The third condition that has to be met is the leading ones have to form a stair-step pattern down and right. Not down and left, not up and right, but stair-step pattern down and right. And it's not going to matter if some of the steps are different sizes, as long as in general it goes down and right. All right, and the fourth condition, the leading one in each row has to be the only non-zero element in its column. Okay, let's see what each of these means. Are the following matrices in reduced echelon form? Okay, so first we're just going to see how to recognize reduced echelon form. Later we'll see how to get reduced echelon form. All right, your first matrix. Is this reduced echelon form? Well, let's check. We have four conditions. Let's check all four. Are the rows of zeros at the bottom? Well, there they are. They're right at the bottom. Yes. Okay, so move to the next condition. Is the first non-zero entry in each row a 1? Okay, well, in the first row, first thing I see is a 1. In the second row, I have to go over 1, but then I see a 1. Okay, so the first non-zero, if I go from left to right, in each row is a 1. So yes. Okay, now move to the third condition. Do those ones form a stair-step pattern down and right? Well, let's check. To get from the first one in the 1, 1 position to the next, I go down and then right. So yes. Okay, we're doing real well. We've met 3 conditions. Is that enough? No, we still have to go to the fourth condition. Is each leading one the only non-zero entry in its column? Well, let's check. We have to go to the places only where we have leading ones. If you happen to have a 1 somewhere else, it's not a leading 1. You don't care about that particular column. Okay, but I see in that first column I had a leading 1, and yes, it's the only non-zero in its column. In the second column, I also had a leading 1. It's the only non-zero in its column. Yes, so this matrix is in reduced echelon form. Okay, so it met all 4 conditions. It's reduced echelon form. Let's look at another example. All right, this time, let's check all 4 conditions again. Are the rows of zeros at the bottom? Yes. Okay, you have a single row of zeros, and yes, it's at the bottom. Next, is the first non-zero entry in each row a 1? Absolutely. There's 1 in the first row, and it said the first non-zero, so you don't count the 0. You're just looking left to right. The first thing you see that's not a 0, is it a 1? Yes. Okay, what about in the second row? Yes, as you're looking left to right, the first thing I see that's not a 0 is a 1. So we're good on the leading ones. Okay, what about, does that go down and right to get from one to the other? You start at the top, you go down, then you go right, yes. Okay, so we've got the stair step down and right. Now it doesn't matter that you have to go right 2 spaces. That's not an issue, just the fact that it goes down and then right. Okay, what about, is each leading 1 the only non-zero entry in its column? Now remember, I only have to check the columns that had leading 1s. Okay, now in the second column, there was a leading 1. It was leading 1 in the first row. All right, also I had in the fourth column a leading 1. It was the leading 1 in the second row. Okay, so is each leading 1 the only non-zero in its column? Yes. So this matrix is in reduced echelon form. Okay, let's look at a third example. All right, this time, are all the rows of zeros at the bottom? Well, do you have a row of zeros? Yes. Is it at the bottom? No. This matrix is not in reduced echelon form. There's no need for me to check right now all the rest of the conditions because, you know, the fact that it failed on 1 means it's not reduced echelon form. Okay, next. What about this one? Are all the rows of zeros at the bottom? Well, there aren't any. Okay, so by default, we're just going to say yes, because, well, you know, they're invisible. So sure, they're at the bottom. Doesn't really matter where they are. There aren't any. Okay, so we just kind of skip over that condition and say, yeah, sure, it meets that condition. All right, is the first non-zero entry in each row a 1? Well, let's look. First row looks good. Second row also looks good. Third row, uh-oh, we have a 5. That's supposed to be a 1. So row 3 failed on that condition. So that matrix is not in reduced echelon form. You'll sometimes see it abbreviated RE form. No need to check the rest of the conditions there. Okay, next example. Are all the rows of zeros at the bottom? Well, again, there aren't any, so we just say yes. What about, is the first non-zero entry in each row a 1? Well, first row looks good, second row looks good, third row looks good. Yes, the first non-zero entry in each row is a 1. Okay, let's check the third condition. What did it say? Do the leading ones form a stair-step pattern down and right? Well, to get from one to the other, it looks like I'm going to have to go down and left. I go down and right to the next one, but I've already failed on the down and right for the first two. So I would just say, no, this matrix is not in reduced echelon form. Okay. Have lots of examples for you because I wanted you to be prepared for this section. Okay, what about this one? Are the rows of zeros at the bottom? Check it out. There's your rows of zeros. It's at the bottom. Yes. Next, is the first non-zero entry in each row a 1? Look at the first row. Okay, I see a 1. So that one's in good shape. Second row, 0, 0, and then a 1. Okay, so that's good. Okay, what about third row? Yes, 0, 0, 0, and then a 1. So yes, everything looks good as far as the first non-zero entry being a 1. Okay, let's keep going. Do the leading ones form a stair-step pattern down and right? Okay, it looks like to get from the first one to the second one, you go down and then right a couple spaces, and then next down and right a couple more spaces. So yeah, we're in good shape there. All right, good. Last condition. Is the leading one the only non-zero entry in its column? Well, let's look at that first leading one. Is it the only non-zero in the first column? Yes. What about the second leading one? Yes, it's the only non-zero in its column. The third leading one? Yes. So I really only had to check columns 1, 3, and 5. Those were the only ones with leading ones. Okay, so did it meet all 4 conditions? Yes, and so it's reduced echelon form. Okay, even another example. Let's check it out. Here I have any rows of zeros? Well, there aren't any, so you just again say yes. All right, what about, is the first non-zero entry in each row a 1? First row looks good. Second row looks good. Third row looks good. Okay, so yes. What about the stair-step pattern down and right? Do I have that? If I go down and then right a couple spaces and then down 1 and then right 1 space. Okay, it doesn't matter that the steps are different sizes. That's not important. Just the fact that it goes down and right. Okay, so yes, it meets that condition as well. Is it going to fail on this fourth one? Let's see. Is each leading one the only non-zero entry in its column? Well, let's check all the places we have leading ones. We had a leading 1 in the first column, and it was in good shape. Second column looked good. Well, it's not actually the second column, but the second leading 1, excuse me, it's the third column. What about the third leading 1? It's in the fourth column. Is it the only non-zero in its column? No. So this is not reduced echelon form. I hope this is making sense. If it's not, go through some more examples, check out the book, check out the presentation online. All right, now that you know what reduced echelon form is, let's see how to use it and how to get it. Solve the following system of equations by using elementary row operations to transform it to a matrix in reduced echelon form. In other words, we want to use Gauss-Jordan elimination, and then reduced echelon form is going to tell us when to stop using the elementary row operations, when to say we're finished. Okay, so let's check out this system. Pretty big system. x1 minus 3x2 plus 2x3 plus x4 equals 14, and then negative x1 plus 3x2 plus x1 plus x3, excuse me, minus 7x4 equals 4, and then 2x1 minus 6x2 plus 2x3 plus 6x4 is equal to 16. Okay, pretty enormous there. Let's first of all start by tossing it into an augmented matrix. All right. As you see on the left side of the augmented matrix, I have the coefficients. On the right side, I have the constants. And it was always a good idea, remember, to make sure that the system of equations was in standard form with all the variables on the left and in order, and then the constants on the right of the equals before I ever try to do this. Okay, now, reduced echelon form. There's going to be a systematic way that you want to go about this. Luckily, it's the same as what you've been doing all along. You've actually been, when you're going for that diagonal of all ones, you've been using the correct order of doing these Gauss-Jordan elimination. So what you would have done is you would have first checked the 1, 1 position to make sure you have a positive 1 there, and you do. But then you move down to the second row, and then where that negative 1 is that's circled, that needs to be a 0. Okay, so I need to figure out how to get that to be a 0. And I also want to get rid of the 2 that's in the third row. I want that to be a 0. Okay, so if I do row 2 plus row 1, and then row 3 minus 2 row 1. That's going to give me zeros in those two positions. Okay, so as far as the Gauss-Jordan elimination part of this, it's the same thing. But you want to start with the first column, make it be 1, 0, 0. Then move to the next place where you can get a leading 1. If you see in the second column, I'm never going to have a leading 1 right there. Okay, so I don't even mess with the second column. The second column is going to stay like it is, other than whatever changes might occur because of, well, actually, nothing's going to happen because you're always going to be adding zeros. Okay, so second column is going to pretty much look that way for the rest of this problem. But the third column, where that 3 is sitting, I could make that a 1, and that would be my leading 1. Okay, so how do I get a 3 to be a 1 without messing up my zeros in front? I'm going to need to do 1/3 of that row. Okay, so 1/3 of row 2. All right, as you see there, it changed my 3 into a 1. Okay, now again, I'm trying to make that second column look pretty now. I've got the 1 where I need it. Now I want to move to where I want zeros. I want a 0 where the positive 2 is. I want a 0 where the negative 2 is. For some reason, when I was writing this up, I decided to do the negative 2, get rid of that first. So here we go. I'm going to make that into a 0. And if you check it out, you've got all zeros across the bottom row now. Okay, row 3 plus 2 row 2 gave us all zeros across the third row. But now I need to get rid of the 2 that was above that leading 1. I need to make that a 0 as well. So I need to do row 1 minus 2 row 2. And that gave me that column being, the third column being 0, 1, 0. So you can check now, does it meet all 4 conditions? Are your rows of zeros at the bottom? Yes. What about does each row, its first non-zero entry, is it a 1? Yes. I've got a 1 in the first row, I've got a 1 in the second row. Do those 1s go down and right? Yes. Do I have that stair step? Yes. What about, is the leading 1 the only non-zero in its column? Yes. Okay. So your goal here is to get a leading 1 in the particular column you're working on, and then eliminate the other entries in that column, making them zeros. And move left to right, of course. All right, let's write out the general solution. You can see that across the top row I have x1 minus 3x2 plus 5x4 is equal to 2. Now remember, our convention in mathematics is we solve for the one on the left. So I'd want to say x1 is equal to 2 plus 3x2 minus 5x4. Okay, in the second row I had x3 minus 2x4 is equal to 6. That leads us to x3 equal to 6 plus 2x4. Okay, so that's our general solution. x1 is 2 plus 3x2 minus 5x4, and x3 is 6 plus 2x4. But remember, we need to account for every variable. This was in a previous section, if you remember. We had something for x1, we had something for x3, but how many variables do we actually have in this problem? Okay, the nice thing about reduced echelon form is that once you have all the equations written out and solve for the one on the left, and it'll always work out beautifully that the one on the left will have a coefficient of 1. It's part of the nice things, one of the nice things about reduced echelon form. Anything that's left out, or anything that's on the right, you can think of it either way. It works a little better if you think anything left out, because I'll show you that situation in a second. Anything that's left out is going to be independent. So you just automatically can say, well, x2 is x2 and x4 is x4. Okay, that gives me my general solution. So I actually have 2 independent variables in this problem. It has infinitely many solutions. Even just one independent variable would have been enough to tell me that. And it has a 2-dimensional solution set. Remember, the dimension of the solution set is the number of independent variables. So there's 2 independent variables, so a 2-dimensional solution set. Okay, let's take a look at the general solution for the system represented by this augmented matrix. Okay. Now, is that one already in reduced echelon form? Let's check. Do I have rows of zeros? No, so I can just automatically say, yeah, they're at the bottom. Is the first non-zero entry going from the left a 1? Yes. Okay, that's good. Do I have the stair-step pattern down and right with my leading ones? Yes. What about the last condition? Is the leading 1 the only non-zero in its column? Look at the first column, look at the second column, look at the third column. That's the only places that I have leading 1s. So I don't have to do anything with the fourth column and the fifth column. So I can say, yes, that is in reduced echelon form. If you're given a matrix that's not in reduced echelon form, your best solution is to get it in reduced echelon form first before you try to write out the system, the solution to the system, because you'll get in trouble a lot of times if you don't. Okay, so this was in reduced echelon form. I can now write out my solution. I'm getting that x1 was 1, x2 is 2, and x3 is 3. Is that it? Looks like a unique solution right now, right? But wait a minute, didn't I have another variable? Didn't I have 5 columns? Okay, they wouldn't have given us something that had 5 columns if we hadn't had 4 variables. Okay, there was an x4 in that system. Okay, that fourth column, wouldn't have been there. I would have just had, that fifth column wouldn't have been there. It would have been over where the fourth column is. So I wouldn't have had that column of zeros at all if there hadn't been an x4. So this system had 4 variables in it. Otherwise, the augmented matrix wouldn't have had 5 columns. Let me say that another time. Okay, so I need to now say, because x4 was left out and I had reduced echelon form, x4 is x4. In other words, x4 is independent. So that system has infinitely many solutions. And since there's one independent variable, there's a one-dimensional solution set. Okay. All right, so that was the section about reduced echelon form. Hopefully you've seen not only what reduced echelon form is, but how to get it and what it does for you. What it's going to accomplish for you is it's going to make writing out the general solution much more simple. You won't get into traps of leaving out variables, maybe trying to say, like on that last example, that something had a unique solution when it actually had infinitely many. Okay, so just remember that once you get an augmented matrix to reduced echelon form, go ahead and write out the equations that you have, solve for the one on the left, and it'll always work out beautifully that has a coefficient of 1. And then any variable left out is going to automatically be independent. Okay? So give this section a try. It's kind of a long section, so you're going to have to spend some time on this section, working on problems. Well, as you saw, we had 3 different things we learned. Not only what it is, but how to get it and what it does for us. So spend some time on it. And once you get this section under your belt, the next section is going to be really easy.